monkey has been trained to catch a banana in mid-flight while free-falling from a 5.2 meter high tree branch. The banana is launched from a cannon located on the ground at a horizontal distance of 9 meters from a point directly under the monkey at exactly the moment the monkey drops from the branch. And this is a classic problem that some of you may have seen before. What you're expected to find are A, find the angle above the horizontal. The cannon must be aimed so that the monkey can catch the banana before hitting the ground. B, find the minimum launch speed of the banana so that the monkey can catch the banana before hitting the ground. And C, if the launch speed of the banana is twice the minimum, how high above the ground is the monkey when he catches the banana? Okay, the way to set this up, first of all, let's take note of the information that we're given. The height of the tree is 5.2 meters. And the distance of the cannon from the tree, or the branch directly measured underneath the monkey, is 9 meters from a point directly under the monkey. So here's how we set this up. Let's move it up here. Let me draw a coordinate system. Okay, here's a coordinate system. This is X, and this is Y. And let's say this represents the line directly under the monkey. Here's the monkey, like this. We'll give him a little tail here. And the monkey is, let's say, at some height h, which is equal to 5.2 meters above the ground. And the distance of the cannon, there's a cannon over here, like this, at the origin. And this distance here, delta x, is equal to, delta x is equal to 9 meters. So what we need to do is set up the equations that describe the motion of the object, both the monkey and the cannonball, which gets fired out like this. Let's say like this. This is v naught, which represents the velocity initially of the cannonball. And I'm going to refer to this as item 1 and this as item 2. So when I write my equations of motion, I can distinguish between what's happening for this object and what's happening for this object. So let's describe the motion of the cannonball. We can write that the y function, the position y is a function of time, y of t for the cannonball, let's call that y1, is equal to minus 1/2 g t squared plus v naught y t plus y initial. Well, let's see, y initial is 0, so I'll just leave that off. And y2, which describes the monkey's motion in the y dimension, is minus 1/2 g t squared plus v in the y direction, which is 0 since he drops starting at v equals 0, plus the initial y position, which is h. So I'll write it like that. So I can also write the equations of motion in the x direction. So x1 of t, which is the cannonball, is just, well, it doesn't accelerate in the x direction, so it's just v naught x t plus initial position, which is 0, so I'll just leave that off. And x2, which is the position of the monkey in the x direction, is just equal to delta x. Or you could just call it x, but I'm going to call it delta x. It's also equal to the range, which I'll call r. So what we know is that the banana has to be shot out of the cannon, make a trajectory like this, and cross the path of the falling monkey, which is like this, at some time t. Well, fortunately, t is the same for the banana and the monkey. We can use that information to solve this problem. So first of all, y1 and y2 will be equal at this point where they come together. So I can write that y1 is equal to y2. So that looks like this: minus 1/2 g t squared plus v naught y t has to be equal to minus 1/2 g t squared plus h. So now I have this equation right here. I have a minus 1/2 gt squared on each side, so those cancel each other out. And I'm left with v naught y t is equal to h. I also know that in the x direction that delta x is just equal to v naught x times t. And from these two equations, I can get the answer I need. Namely, from this equation right here, let me see if I have enough room here. Let me move this up a little bit. Move it up to here. So I have from this equation, I have that t is equal to h divided by v naught y. And from this equation, I have t is equal to delta x divided by v naught x. So this t is equal to this t when they collide with each other. So I can write that h over v naught y is equal to delta x over v naught x. Or I can also write that v naught y over v naught x is equal to h divided by delta x. And that means from these two, v naught y is v naught times sine of the angle theta, which is this angle right here, divided by the x component of the velocity, which is v naught cosine theta, like this. And consequently, the v naughts cancel out, and what I'm left with is sine theta is equal to h over, I'm sorry, not sine theta, but sine theta over cosine theta is equal to h over delta x. And that means that the tangent of theta, which is just sine over cosine, is equal to h over delta x. And that means that theta is equal to the angle whose tangent is h over delta x. And you'll notice, we go back and look at the picture up here, that what that means is this is the height h, and this is delta x, and that forms a triangle like this. So that means that you aim the banana directly at the monkey. It's not the way I've drawn it in the picture here, but that's the idea. So if I want to find out exactly what that angle is, I have to get my calculator and plug in the numbers, which I'll do that now. So theta is equal to the angle whose tangent is h, which is 5.2 meters, divided by delta x, which is 9, like that. And that means that theta, here, let's put it in here and see what it looks like. 5.2 divided by 9 equals, and then the inverse tangent gives me 30.01836 and so some other digits for the answer. So I'm going to store that in one of my memory locations. But it's about 30.02, approximately 30.02 degrees. And that's the first thing that we wanted to find, is what is the angle at which you need to aim the banana cannon. For the second part, let's go back and take a look at that. The second question is, find the minimum launch speed of the banana so that the monkey can catch the banana before hitting the ground. And what that's saying basically is that if I don't launch the banana at a fast enough speed, even though I have it at the right angle, it's going to go up here and fall short somewhere. It's never going to get to the monkey. So I need to find out what the minimum launch speed is so that the banana can actually get to the monkey. Obviously, if I launch the banana at such a velocity that it gets to the monkey right here, then that represents the minimum velocity that I can use to get to the monkey. And we already have an equation for that measures the range delta x or the range r. And to refresh your memory what that looks like, that looks like this. R, the range, is equal to v naught squared over g times the sine of 2 theta. So we can solve this equation for v naught and write it as g times r over sine of 2 theta, square root of that, and not approximately, is equal to v naught. And this is the minimum velocity that we need to give it in order to make it over to the monkey. And that's equal to, putting the numbers in here, 9.81 times the range, which is 9, divided by the sine of 2 theta, which is 60.04 degrees. And then take the square root of that. To put that in the calculator, I'll put it up here where you can see it. First of all, I left the 30 degrees in there, roughly 30 degrees. So I'm going to double that. That's my 60.04 degrees. And I'm going to take the sine of that, and I'm going to divide that by 9.81 and divide that by 9. That's equal to that. Now I have to flip that upside down, so I'll use 1 over x to do that, and then take the square root of this number, and I get v naught min is equal to 10.095 plus some other digits. That's approximately equal to 10.1 meters per second. And that's the answer to the B part of this problem. Okay, so let's look at the C part. If the launch speed of the banana is twice the minimum, how high above the ground is the monkey when he catches the banana? So how do we do that? Well, first of all, we have to figure out how long it takes to get from here to here, or to here where they collide, if it's twice as fast as the minimum speed. So how do we do that? First of all, then we look at the x component of that speed. So v naught x in this case is equal to 2 times this v naught min, 2 times 10.1 meters per second times the cosine of 30.02 degrees, and that's approximately equal to, let's put the calculator up here again so you can see it. First of all, that was the speed that we came up with. Multiply that times 2, and then multiply that times the cosine of this 30 degrees. I have to recall the cosine, take the cosine of that, times 17.48 equals, the 20.2 approximately, and that's equal to 17.48, approximately 17.48 meters per second. That's what V naught x is. But I know that delta x is equal to V naught x times t. So t then is equal to delta x over V naught x, and that's equal to 9 divided by V naught, which is 17.48 meters per second, and that's approximately equal to, well, I still got it in the calculator, so I'll divide that by 9 and flip it upside down, and that's equal to 0.5148 plus some other digits. I'm just going to leave that. I'm going to store that in one of my locations. Store that in location number 2, let's say. So now what I have to do is take the equation for the monkey, the y equation for the monkey, y2, which is equal to minus 1/2 g t squared plus h, and plug into it the time that has elapsed since the banana left the cannon, which is right here, when it's going twice as fast as the minimum speed. So that's equal to minus 1/2 g, which is 9.81, times t, which is 0.5148 plus some other digits squared, plus h, which is 5.2, and that, let's see what that works out to be. First of all, the time is still in there, so I'll go ahead and square that. Multiply it times 9.81 divided by 2, and that's equal to this number. I'm going to change the sign of it because of this minus sign right here, and then add it to 5.2, and what I get is 3.9. So this is 3.9 meters above the ground. And this is what was asked for in part C of this problem.